Today I'm going to tell you about origami in engineering. And this is valuable because we work with highly complex design problems. And the approach that I'm going to show you could help you solve some of them. But at the very least, what I'm hoping you take away from this is an understanding that you can use origami to discover engineered designs. Origami began as a Japanese art, which is cool. But then it got even cooler because the mathematicians got involved. As soon as you apply math to something, its usefulness grows, to the point where origami artists were able to create amazing new pieces. And engineers they gained new capabilities that extend into all kinds of areas like automotive, consumer products, architecture. There's also space, medicine, robotics, the list goes on. So how do we get these capabilities? Well, I'm going to demonstrate this with a few examples, and then, first actually I'm going to give you the tools right now. A good place to start with this is with existing origami crease patterns. It's a simple idea, yet very powerful, which you'll soon see. You can also create new crease patterns using software. Here's a list of softwares that will do things like generate crease patterns that will then fold into given three-dimensional geometries, or simulate folding, or help you to analyze the kinematics or motions of your designs, which leads into my research. What I do is discover mechanisms in origami. If you take a simple crease pattern like this one and fold it, you'll begin to see some similarities with rigid mechanisms. In fact, it does basically the same thing. And you can get here with almost any crease pattern simply by reducing it down to its basic folds and facets. And from that point, it's just a matter of tweaking it to fit your design needs. So now we have these three tools. We have existing crease patterns, new ones, and kinematic analysis. We're empowered. So let's see some examples. In this case, we had some useful crease patterns and law enforcement officials who expressed to us a need for shielding that had greater coverage and was lighter weight. The result? This folding bulletproof barrier. Folding also works great in space applications because you need to get something that's going to be enormous into space in a lightweight, compact package. This solar array is capable of producing 2 times the power of all of the panels on the International Space Station combined. Heart stents save lives, but they have a couple of issues. One is restenosis, which is when tissue grows back through the mesh over time, reblocking the passage. Deployment can also be tricky. Origami made it possible to design this stent graft that combats both of those problems. It prevents restenosis and is self-deploying. Similarly, minimally invasive surgery is saving lives, and it got there by pushing for devices that are more precise and much tinier. What you see here is called the Oriceps, or the origami forceps. And with this, you begin to see the mechanisms behind the folds. This is actually based on that mechanism animation you saw earlier. And this provided the inspiration for a pair of minimally invasive forceps that are a fraction of the size of what's currently available. My final example is cool because it demonstrates all the tools we've talked about so far. It uses new crease patterns, existing ones, and kinematic analysis. Sometimes you need devices that have complex movements, and sometimes assembly can be tricky. These self-folding robots demonstrate that origami is capable of solving hard problems like these. So what you see is that origami is useful in engineering. It's lightweight, it's scalable, it's inexpensive. Origami is no longer just an art. It's a powerful design tool, and it applies in more places than you'd think, and probably in a lot more places that we haven't even thought of yet. My name's Trent Zimmerman, and I represent BYU. Thank you.